All right, our next concept in this unit in equilibrium and acid and base specifically is mainly a lot of mathematics. You're going to want to make sure to have your green sheet available as we go through these different topics. But a lot of these equations are on your green sheet that you can utilize to calculate the pH and pOH of a solution and determine if a solution is acidic, basic, or either neutral. All right, first of all, water is an amphoteric material, which means it can act as either an acid or a base. Water has the ability to donate a proton, and therefore it'll become the hydroxide ion. Again, an acid becomes a conjugate base. Or water has the ability to accept a proton and then to become the conjugate acid, hydronium ions. So water has the ability to act both as an acid or a base, donating protons or accepting protons, which again is one of the many valuable properties for water. Well, the first thing we're going to look at is the autoionization. Auto meaning self, the self-ionization of water. When you have pure distilled water, not every single molecule in the container is actually H2O. Two water molecules can collide with each other and they form one hydronium ion and one hydroxide ion. They form equal amounts of each, a 1-to-1 ratio. And because it's a 1-to-1 ratio, this is still a neutral solution because we have equal concentrations of the acidic particle, the hydronium ion, and the basic particle, hydroxide ions. Okay? Now, if I were to write the equilibrium constant expression for this, Kc, on the top, we would have the products, which would be the concentration of the hydronium ion and the hydroxide ions. Again, ions are always placed in equilibrium. However, on the bottom, there would be nothing. There would be a 1. And that's because the water molecules are liquids and therefore not part of the K expression. This specific Kc has been given a name called Kw. And on your green sheets, you'll see Kw. Kw is the self-ionization constant of water. For any solution at 25 degrees Celsius, the product of the hydronium ion concentration and hydroxide ion concentration will always multiply to the value of 1 times 10 to the negative 14th. Always. Doesn't matter if it's a very strong acid or a strong base, the hydronium and hydroxide ion concentration of any aqueous solution will multiply to 1 to the negative 14th, even distilled water. Okay? And this is called the ion product constant of water. Okay. One thing that is known is that the value of Kw increases as temperature goes up. What does that tell me about the self-ionization of water, the ability of water molecules to collide and form hydronium and hydroxide ions? Whenever there's a direct relationship between the K and the temperature, that tells you that it's an endothermic relationship. So the warmer the water is, more and more of the particles in the solution are hydronium and hydroxide ions. They, again, just so happen to be in a 1-to-1 ratio. Now, one thing you're going to hear me say often is, again, H plus is synonymous with H3O plus, as I said in the first lecture. So again, doesn't matter what it is. The hydrogen ion by itself is usually very much quickly gobbled up by water molecule to form hydronium to stabilize it. So again, whatever the hydrogen ion concentration is, it's also the same as hydronium ion concentration. Okay? Now, in an acid solution, in an acidic solution, the amount of H plus in the solution will be greater than hydroxide ion. In a basic, it'll be the opposite. Hydroxide ion will be a greater concentration. Because, again, as one goes up, the other has to go down in order for them to multiply to the same number. In a neutral solution, the amount of H plus and OH minus are equal. So real quickly, look at this pictorial example that I drew over on the side of a solution and tell me if this is an acidic solution or a basic solution or a neutral solution. Well, these guys that I'm circling are just ordinary water molecules with a oxygen atom, which is bigger than the two hydrogens, in a bent structure. The particles that are unique is this one right here, which is a hydroxide ion, and there are two hydronium ion concentrations. So the hydronium ion concentration is greater than the hydroxide ion concentration, and therefore this would be an acidic solution. So again, whichever one is in higher concentration is the one that tells us if it's either acidic or basic. Okay? All right, now in this next part, we're going to try to calculate both the hydrogen ion concentration, hydroxide ion concentration, knowing one of the others. Well, in the first one here, I know the hydroxide ion concentration is 1 to the negative fifth. If I know the hydroxide, I can always figure out the hydrogen or hydronium ion concentration, doesn't matter, by using the Kw equation. So since Kw is always 1 to the negative 14th, if I know one, I know the other. So here we get the value of 1 times 10 to the negative 9th molar. 1 to the negative 5th is bigger than 1 times 10 to the negative 9th. The hydroxide ion concentration is bigger than the hydrogen ion concentration. This would be an example of a basic solution because 10 to the negative 5 is much bigger than 10 to the negative 9th. Okay? All right. Real quickly, go ahead and pause the lecture and do B and C, please. All right, so for the second one, you should have had 1 times 10 to the negative 7th. This is the concentration whenever we have a neutral solution. There will always be 1 to the negative 7th, both equal, in order to get 1 to the 10 to the negative 14th. If I have a 10 molar H plus concentration, dividing 1 to the negative 14th by it gives me a value of 1 times 10 to the negative 15th molar hydroxide. Again, both the H plus and the OH minus should always multiply to 1 times 10 to the negative 14th. Okay? Now, what happens when I have a acidic solution and not specifically H plus or OH minus? HCl is a strong acid. What does that mean? A strong acid from Unit 2 did not mean that it necessarily has got a lower pH than something else. What a strong acid indicates is that it completely dissociates. So because it's a complete dissociation, 100% of the HCl is actually converted into H plus and Cl minus. So for strong acids, whatever the label on the outside of it reads, if it says 0.10 molar HCl, that also tells me that it's, that it's 0.10 molar H plus. So therefore, I immediately know the H plus concentration is equal to the concentration if it's a strong acid. Now that's not the case for weak acids, and that'll be our next lecture. For strong acids, the concentration on the label tells me the concentration of the H plus. So now to find the concentration of the hydroxide ion, we'll divide the Kw by the H plus. And this would be the concentration of the hydroxide ion. So again, for strong acids or strong bases, if it's a strong base, the label on the molarity of the base is equal to the concentration of the hydroxide ion. If it's an acid, the concentration of the acid is equal to the concentration of H plus in that solution. Okay? We've already talked about how the auto-ionization of water is endothermic, and that's because as temperature goes up, K goes up. Okay? So I'm going to drop down now and look at how to calculate pH and pOH. On your green sheets, you have the equations given right here, which is the base 10 log of the H plus concentration. Okay? So if I know the H plus concentration, if I simply take the negative log of the H plus concentration, and again, I could also have that be the H3O plus concentration, it's the same thing, that is going to give me the pH of the solution by simply taking the negative log of it. We don't have to worry about changing bases. We have to just simply punch in a calculator, negative log, punch in the number, and equals, and that'll give us the pH. Okay? One key thing that students often find difficult, remember the pH scale typically goes from 0 to 14. The lower it is, the more acidic it is. The higher it is, the more basic it is. In the middle, 7 is neutral. So the higher the pH, the less acidic it is. The closer and closer we get to 14, the less and less acidic it is, and the more basic it is. So don't think that the higher the pH, the more acidic the solution. You've always got to think backwards there for it. If the pH is less than 7, it's acidic. If it's equal to 7, it's neutral. And if it's greater than 7, it's basic. We can also calculate the pOH, which is often something that you don't really hear much of, if at all, even in your lifetime. But a pOH is just like a pH, but it's now the negative log of the hydroxide ion concentration. So typically we're worried more about the H plus concentration just because it's the one that we look at, but the hydroxide ion would be just equal to that value. ClO4. All right, turning the page. So it says calculate the pH and pOH of each of the following solutions. All right, so first of all, this is the hydroxide ion concentration. So the first thing I'm going to be able to do is calculate the pOH. So negative log of 1 times 10 to the negative third. Go ahead, punch it into your calculator, and you end up getting 3 exactly in the head. Whenever you take a base 10 log of something to the 10th power, immediately the answer is the negative 3, and then the negative cancels out, and so we get 3. So the pOH of this solution is 3. One other key piece or equation that's on your green sheet is the pH and the pOH of the same solution. Have to be the same solution. The pH and pOH of the same solution always add to 14. So now if the pOH is 3, the pH has to be 11. The pH and pOH of the same solution will always add or summate to 14. All right, go ahead now, pause lecture, and go ahead and give it a try for letter B. All right, the negative log of 1 is 0, so the pH is 0, and the pOH then is 14 because the two of them have to add to 14. Remember I said the pH scale is typically 0 to 14, so 0 is very acidic. It is possible to have pHs even less than 0. We can have some very strong acids with very high molarities be below 0. It's not very common, but it is possible. So don't ever be shocked to see potentially a pH in your lifetime that is less than 0. It is possible. But if the pH, let's say, for example, would be negative 1, the pOH of that same solution then would be 15. So the pOH can go, or actually the pH can go even above 14 on very basic solutions. But again, the two of them must always add to 14 no matter how acidic or how basic the solution is. Okay? All right. So the next one says, what is the pOH if the pH is 6.2? Well, that's very simple. You just got to subtract. And we get 7.8. I always recommend that you convert it to the pH to determine if something is acidic or basic. Too often students screw it up, but for something that's very acidic, the pOH is going to be much greater than 7. So I always like going back to the pH to determine any type of questions on acidity level of a substance. All right, so what I'd like you to do now is to pause the lecture and go ahead and try to do A and B for the following reactions, and we'll see what you get when you restart the lecture. All right, in the first problem A, we just have to take the negative log of 5 times 10 to the negative 3, and we get the pH of 2.30. Subtracting from 14, we get the pOH of the same solution to be 11.7. Again, the two of those numbers must add to 14. In the second problem, we are working the equation backwards. And this is an equation that I circled right here that is not on your green sheet. But if you look at your log button on your calculator, you'll notice that the second function of that is 10 to the caret symbol, or the 10 to the power. So your calculator always tells you the answer as to what the inverse or how to do the reaction backwards. So 10 to the negative pH gives you the H plus concentration. So you type in 10 to the power, and then you plug in negative 7.4, and that'll give you a value of 3.90 to the negative 8. So again, this is an equation that is not given to you in the green sheet, just like 10 to the negative pOH will give you the concentration of OH minus. Both of these equations are not on the green sheets, so if you take the national exam, this is one that you have to remember just how to use the second function of the key, which is just like E and ln. The second function or the inverse function is always the opposite or second function of your key on your calculator. Doing the same thing, if I subtract 14 from 7.4 to get the concentration of OH minus, the pOH is 6.6. 10 to the negative 6.6 gives me 2.51 to the negative 7th molar. Multiplying these two numbers together gives me 1 times 10 to the negative 14th. This is just to prove and check to you that no matter what the substance is, when you multiply the H plus and OH minus concentration of an aqueous solution, it should always multiply to 1 to the negative 14th. That is a constant. Okay? All right, last couple examples here. What is the pH of a 0.04 molar HClO4 solution? Again, the first thing you want to ask yourself, is this a strong or weak acid? And hopefully you said strong. So, perchloric acid completely ionizes, and that makes this problem very simplistic. Since the label says this is 0.04 molar, 1 H plus is produced for every, and therefore the concentration of the H plus is also 0.04. So when you have a strong acid, the concentration of the H plus is equal to the concentration of the label of what the acid is. So therefore, the pH would be negative log of 0.04 molar, and we get a pH of 1.40. All right, again, I'm going to pause the lecture. This is your last problem for today. Calculate the pH of a 0.028 molar sodium hydroxide solution. And sodium hydroxide is a strong base. So go ahead and see if you can figure this out. And again, I'm going to pause the lecture and let you go ahead and work on that. Restart it when you are finished. All right, since it's a strong base, sodium hydroxide will completely dissociate, and therefore 0.028 molar sodium hydroxide will produce 0.028 molar hydroxide ions in the solution. Taking the negative log of that, that gives me the pH of 1.55. I'm not done here. This is where often students tend to stop, but we're not there yet because that's not the pH, that's the POH. So 14 minus 1.55 gives us a pH of 12.45. So for strong acids and strong bases, it's pretty simplistic. If it's a strong acid, the concentration of the acid is also equal to the concentration of the H plus concentration, so then we can easily figure out its pH. If it's a strong base, we know the hydroxide ion concentration, and then can go through the steps to figure out the pH of that solution as well. So that's how we calculate pH and POH. I have some practice problems in Canvas I'd like you to go ahead and try and do a bunch of practice off of. And then that gears us up for next week, which is now looking at weak. What happens when we have a weak acid and weak base that doesn't completely dissociate? What can we do to figure out what the pH of those solutions are? And that, again, is utilizing ice tables and ice tables of Ka, weak acids, and Kb for weak bases. And that'll be the next lecture for this topic is. Again, thanks for listening.